To take care of any questions you had about homework problems that you worked on. So we will start with the reading. Tell me about the reading. What did you learn? What are you curious about?
Really? Can you tell?
I think it is one. Yes, sir.
Financially, if we were to do that every day, it would be a waste of 1.5 grand.
Yep, that's right.
Because the tuition you pay by class, and so then we add up the time for everybody or something, and then
Per year.
equates to $1,400.
1440.
There you go.
Okay, either way.
So, questions about reading? What did you learn? Reading this for a second time.
It's hard to do it.
You knew the whole thing,
Not the whole thing.
and you reread it and learned nothing.
I didn't find that.
So what did you learn?
Use the table.
Okay. What'd you learn?
Reading the stuff. What you can understand more about the problems.
Okay.
So, whenever I would get the problems, I didn't know what to do first.
Good. So it was helpful. Somebody summarize what she's saying. What did the reading help her with?
We couldn't hear it up here.
Oh, okay. Can you say it again louder, please?
I could solve the problems by steps.
That's a good summary. What'd you like?
I guess I learned like different ways of organizing the equations, like rewriting them.
Okay. Give me an example of that.
Like normally I just do like change in kinetic plus change in energy equals 0, but they do it like they do like kinetic 1 and then potential 1 equals 2 plus potential 2.
Like that. Yes. Good. And this is an example of what we were talking about yesterday, where they take the same equation and they express it in a different form. Because actually, if you think of delta K as final minus initial, right? And you think of delta U as final minus initial, and take this guy and add K1 to both sides and add U1 to both sides, then you get this equation right here. So they are the same equation expressed differently in symbols. It's saying the same thing. Why might we want to express an equation slightly differently if it's saying the same thing?
Sometimes it's easier to put it together.
Yeah, it's all about convenience. That's it. Good. Good. What did you learn from the reading? Blake.
I didn't do it.
Tommy.
Well, I went over how the network equals the changing kinetic energy, and then how you can use the different formulas that add up to each other.
Good. Good. What did you learn from the reading, Lydia?
I was going to say about work, like non-systems, and I can recommend something that
Okay, great. Yeah, so let's talk about that a little bit. What you're really talking about is the computation of work. How do I compute work? Okay? And so let's start with our basic formula. Work equals force times distance times the cosine of the angle between. And this formula right here is useful when my force is a constant value, a constant number. And the way in which I use it is I identify my force vector, and I identify the distance or displacement, really, that we're traveling, right? And I actually draw those, and I say, what's the angle between those? And now I've got all the values that I need for computing. So here's some good examples of this. Let's say I have a crate on an inclined plane or something like that. And I want to know how much work does gravity do as the box slides down a distance d. Okay? So I draw for myself the force of gravity, which of course always pulls
Down.
and now I say mg is like so, and d is like so, and let's actually, okay, so this angle is theta right here. I want to know what's that angle right there. And I see a right triangle, and I recognize these are complementary. So this guy would be 90 minus the angle, whatever that is. And so now I get an expression for my work. The work is equal to mg times d times the cosine of 90 minus whatever that angle is, just like that. Is that the kind of thing that you're talking about?
I was talking about non
Ah, okay. Well, let me say just a little bit more about the computing of work, and then we'll specifically address non-conservative forces. If F is not constant, such as we had with our Iron Man problem on the exam, then you're going to have some relationship between the force and the distance, right? And that relationship will come in the form of some kind of graph like that. And now, if I do force times distance for each little bitty piece of distance that this thing travels, and on each little bitty piece of distance, if I pretend that the force is basically constant, then what I get is the area under the curve, like that. So the area is equal to the amount of work done. But I still have to pay attention to direction, right? Because it could be positive or it could be negative. So work equals area. And that's how the computing goes. Now, what about conservative versus not conservative? I want to go back to what we had here. We had two really big ideas. One of them is that delta K plus delta U equals 0. And this was the expression of the conservation of energy. Like so. And then here we had net work equals change in kinetic energy, which is an expression of the work energy theorem. Okay? How do we put these two together? Well, we would put these two together by setting equal things equal. So here I have work equals delta K. Up here, what is delta K equal to? Close. Very close.
Teachers,
Negative.
pardon the interruption for this mid-class announcement. The varsity girls basketball team will be off today, no practice.
Just
Today's games
everything
for
is-
varsity boys and JV boys will be postponed until Tuesday. The JV and varsity boys basketball will have practice at 3:15 and 5. Cheerleading will not practice. Please, cheerleaders, you will dismiss at 3 o'clock. Tomorrow, the the building will be closed. There will be no drama practice, there will be no robotics. Robotics qualifier will be canceled. It will compete again on the 31st of January and February 8th Sunday to qualify for states. The JV and varsity boys basketball games for tomorrow are canceled. And there is no girls basketball practice tomorrow. So basically everything's canceled.
Yes. So, yes, sir. Yes, not the 7th. You got to eat. They put it on Sunday the 8th. Thanks. All right. So we have network is equal to the opposite of the change in potential energy for conservative forces. Okay. What about non-conservative forces then? Non-conservative forces simply do not have a potential function, and so we can still compute work as force times distance, we just can't use potential energy to compute it. That's the only limitation, and that's the only difference. Yep. So for non-conservative forces, there is no potential function U for those non-conservative forces. But everything else is still in operation. We still compute work equals force times distance, and the work still equals the change in kinetic energy. So let's actually do an example of this, so that we can see it. Let's somebody come up for me with a situation in which there is a conservative force and a non-conservative force acting. Make up a scenario. A roller coaster. Great. So we're going to have a roller coaster. And just for the fun of it, how can we make this situation fairly simple? What path should our roller coaster take?
Straight down.
Like circle? Could be a loop. Okay, let's do a circular loop.
Okay.
Kick off the acid.
Oh. I wasn't. Let's do a simpler. Let's do a simpler scenario. Yeah. How about just down? How about down and an
Yeah, I
angle?
like just straight down.
Well, just straight down could be cool, except that if we do, then what's our non-conservative force going to be?
Gravity.
Now that's conservative. Air resistance? Okay, we can do air resistance. We'll do air resistance. Fine.
With air resistance, I got zero.
So, we all get to travel on the coaster of doom. Of doom. Of doom. We need a number. How high is this going to be?
3,000 feet.
Please, meters. 100 meters. 100 meters. 100 meters is enough to get you screaming. All right. And we need a mass for our coaster.
How like 100? Is that a lot?
100 what?
Kilograms?
100 kilograms. So about 220 pounds.
That's one.
That's really light.
That's one guy.
One guy.
Oh, wow.
We'll make it 1,000 kilograms, which is still pretty light, but you know, there it is. It's a single cup. All right. So now this guy is going to drop. Now the thing that we don't know about is air resistance, so I'm going to supply some information. We're going to pretend that the air resistance is going to be 2,000 newtons pushing up.
That's pretty heavy air.
Let's just stop blocking.
And this is actually an average force. In real life, what would happen is the air resistance would be 0 at the top while it's not moving, and then it would increase as it goes faster and faster. So I'm just going to pretend this is an average force here. And now, we're going to experience a force straight down of gravity, and we're going to ask, how fast is this going at the bottom? Okay. And we can approach this in two ways that mean exactly the same thing. One is to simply use work energy directly. And if we simply use work energy directly, we say that the net work is equal to the change in kinetic energy. And the net work is going to be equal to 10,000 newtons pulling down times the displacement, which is 100 meters, times the cosine of the angle between. My displacement is in this direction, my 10,000 newtons is in this direction, therefore we have a cosine of 1. Right? Plus the 2,000 newtons of air resistance times the 100 meters times the cosine of the angle between, which is -1, because my force is pointing up and my displacement is going straight down. Right, we're doing net work. And so we subtract those. And all of that is equal to the change in kinetic energy, which is 1/2 of 100 times v squared minus the initial kinetic energy, which is 0. 1,000, thank you. Good catch. Okay? And so now when I do this, it's a fairly simple thing. I'm going to get 10,000 times 100 minus 2,000 times 100 is 8,000 times 100, or 800,000 newton meters of work done on this thing. Please do not stand under it. Is equal to 1/2 of 1,000 v squared. What's the most efficient way to solve this equation in your head? Divide by 1,000 first. Right. Multiplied by 2. So v squared is equal to
1,600.
and v is equal to
40.
40. Yeah. V is equal to 40 meters per second. So that's how the work energy would go. The second way that I could think about it, which is exactly mathematically equivalent, it's the same thing but spoken a little bit differently, is to use the idea of the chart and do U and K at the top and at the bottom. And if I do the U at the top and at the bottom, exactly. So the reason that I picked this example is we have one conservative force, which is gravity, and we have one non-conservative force, which is the air resistance. So we're going to consider only the MGH, which is 100,000 joules. And our chart is fairly easy to fill in. And now here's where the non-conservative part comes into play. When I add up these two quantities in the table, they're not equal because we have a non-conservative force acting on it. Exactly. So that the difference in energy is equal to the amount of work done by the non-conservative forces. The difference in the total, which is going to be 1/2 times 1,000 v squared minus the 100,000 that gravity supplied, equals the work done by the non-conservative force, which we already saw was negative, what was it, negative 20,000? Negative 200,000, and I missed a 0 on this guy. This is a million here. There. Now, if you take a look at this equation right here, this equation is algebraically equivalent to the one that we had before. All I have to do is to add 1 million to both sides, and I get exactly what we got before. 1 million plus negative 200,000 is going to be 800,000, and then we do the same solution. So all that we're doing is doing the same accounting, we're just counting it up slightly differently. In the first case, we're saying we don't care whether our forces are conservative or not, we're simply going to add up the total work done, and that equals delta K at the end. In the second case, we're going to say, let's take a look at all the types of energy that are conserved, and the difference in that energy, which I wrote really badly here, looks like a K, but it should be E. There we go. our difference in energy between the two has to be the work done by the non-conservative forces.
But in the book it just says the beginning plus or equals after.
Which is the same thing. Good, you're starting to see this. That's right, because this is final minus initial, right? E minus E0. And so if I add to both sides, then I get this, and I'm guessing that's what the book has to say. Is that right? Or do they do it as U plus K and U0 plus K0?
You have a long
Oh, here. Okay. I have delta G, and E is the K plus the potential together. Yep.
sorry.
Yeah, so that's one of the things that confuses people about energy sometimes. And that is that fundamentally you want to think of the total mechanical energy as potential plus kinetic, right? So when I do find the change in the energy of an object, I have to account for its change in its potential plus its change in kinetic. And that's what they're expressing in that equation. Good. And these kinds of questions are really important because, as I said before, a lot of times they'll simply change symbols on you and you're thinking, what happened here? Well, nothing. It's fine. They're just expressing different symbols. Good. Other questions? More homework questions? Yes, sir.
I went through, but I would just like to go over just so I fully understand 52.
52. Swing. So we have a 110 kilogram crate, that's the one? Starting from rest, pulled across the floor with a constant horizontal force of 350 newtons. Hopefully your free body diagram starts like this. For the first 15 meters, the floor is frictionless, and for the next 15, the coefficient of friction is 0.3. What is the final speed of the crate? Oh, they did that to us, didn't they? Okay. Great. So this is a diagram that expresses the problem as stated. And so, Joseph, what did you do with it?
Well, first of all, I tried, because I'm trying to get the full speed, I did work net, the network, and the change of kinetic energy, so I did kinetic final to kinetic initial. So, you know, I did the works, both of them, as force times distance times the cosine angle, and the first one being 0. And then, well, I did that for friction, I did that for the force as well.
Good. Let's do the right-hand side because it's easy. How did you represent the delta K?
So again,
The right-hand side. How did you represent the delta K?
Well, first off, I did I put them into K1 and K2. K2 take K1.
Okay.
And then because it's not originally moving, K1 equals 0.
Good.
So all this kind of, so then I kind of first did the working out of the friction and the force before I put it in.
Sure. What am I going to put in here for K2 though?
1/2 mv squared, or,
Do you know any of those numbers?
well, the n being 110.
Yes. Right. And since we don't know the V, then we don't panic. We just write that as V squared. Good. Okay, now let's come over and focus on the net work here. And tell us about that.
So this be the stuff with like the friction again, or? The frictional force is, well, F times D times the cosine 180, so it'll be negative force times distance.
Okay?
Um,
I agree with that. Keep going.
Then couldn't we substitute numbers into that? It would be 3 and, would it? Well, I know D is probably 15 because it only acts on 15 meters.
That's a really good point. Yeah, that's right. Your D is going to be 15. What's your frictional force?
Would we have to use the sum of all, or would it just be 350 in the opposite direction?
That's a really good question.
Yeah.
He is confused about what the frictional force would be. Somebody tell me what thing needed to happen for him not to be confused here. What's that? What's that? Labeling. Some things need labeling.
I was gonna say that if you look at the equation for friction, you see exactly what happens.
Okay. Yeah.
The first 15 meters of friction, so it's just FD cosine theta. And then the second one is FD cosine theta over 3D. So you add both of them together.
Okay. All right. He needs a basic tool to clear away his confusion. Yes, say that louder.
Free body diagram.
Did you do a free body diagram?
Not a well enough to find one.
And there's your problem. If you do a free body diagram, it will clear away your confusion. And James had some good advice for you also. If you look at the equation for friction, it will clear away the rest of the confusion. Okay? Okay. So I'm going to leave that to you to do, because I think at this point you've got enough information to go on. This was a key insight, and this is very good. The frictional force is going to only operate over 15 meters. Guys, in calculus, think about it like this. The friction is really a piecewise function, right? It's 0 for the first 15 meters, and 0.3, mu is 0.3 for the next 15 meters. And so when I multiply that times distance, I get 0 for the first part, and friction times 15 for the next part. Does that make sense? Great. Other questions? Which problem was the most challenging for you of the ones that you worked? Charles.
Out of the 4 I did,
Uh-huh.
I thought the hardest one I did was number 54.
54. And what did you learn from that problem?
I learned that I had to utilize the conservation of energy with gravity and friction.
Okay. Now you say conservation of energy with friction. That's an odd thing.
Yes, because I was doing the conservation of energy, and then I realized I had to add on that frictional force.
Good. Yep. Cool. So you saw that clearly. Yes, sir.
This is a random question, but will the final exam have this on it, or will it be second semester?
The final exam focuses on second semester, but you really can't get away from mechanics much, so it'll be there in the background.
But it'll be like, wait, like, will it be like, we'll need this stuff to get us through second semester, or we'll have questions like based on first semester?
You'll need that stuff to get you through.
Right, okay.
Mechanics specific, what about
Mechanics
mechanics
would be
for?
Yeah, all of
What about
that.
circular stuff? Will we need to get circular stuff?
Yeah, we'll see again when we do magnetic field.
Yeah.
Okay, let's see. Delilah, most interesting question you did.
Well, interesting, I don't know. I did 49 because I remember doing it in class together.
Yeah.
And how it was making it's got three different parts because it has the sphere at the top, the bottom, and then a distance after that.
Yeah.
So I redid that because I had done it 2 times before and I still needed to do it again to make sure.
Okay, did it make sense this time?
Yeah.
Cool. Good. Isn't it nice to see process? Love that. So I have the most interesting question. This one here. Did you run into the same puzzle that Joseph did?
Yeah.
Did anybody do 55? Nobody did 55? Okay. Well, I want to tackle 55 just because it reminds us of some things. Now, this is a level 3 problem, so maybe some of you went, but,
A little symbol just makes me not want to.
all right. Well, let's do that one together. Well, we have at number 55, a 0.62 kilogram wood block is firmly attached to a very light horizontal spring. And I'm going to represent the spring, the block as having mass m rather than 0.62. And it's attached to a spring with a spring constant of k. And the deal is they throw in the whole enchilada.
They literally make a lot.
No. They have us compress a distance d from equilibrium. And now they release it. When they release it, it fires off this way. But what happens is it gets out to a distance d1, which I've drawn badly because d1 is substantially less than d. And it stops and it turns around. And now they ask the question, what is the coefficient of friction between the table and the block? Notice that this is a really good example of a question that we could possibly encounter in real life. Because you can picture yourself, you've got a block, and maybe it's part of a toy or something. And you squish it like so, and you let it go. And what you're expecting is if you compress it 5 centimeters, it ought to go 5 centimeters in the other direction because you're thinking conservation of energy, right? And instead of going 5 centimeters, it goes 2.3. And you're thinking, what happened here? And the only possible answer is that something took a lot of that energy away. And so the question is, what took that energy away? So, how might we go about finding out? Yeah, muse is the answer to that, right? How might we go about finding out how much energy was taken away by friction?
By finding the normal force.
Good. Yeah.
You still have equal color, then add in 5. You just
That's the basic right idea. Now we just got to clean that up. Yes, that's right. She said, I just asked that question. How do you deal with non-conservative forces? Well, what's the answer to that
Well,
question?
you have to like you just do the kinetic energy and just
Yeah, that's right. Let's identify 2 points for doing our energy accounting, and I kind of like those 2 points. How much energy is stored up in the spring at this point right here? I call that 1, I call that 2. U1 is equal to what? 1/2 k x squared, but what's the x at this point? It's d, that's right. And how much potential energy do we have at point 2? How much potential energy do we have? d1 squared, 1/2 k d1 squared. And how much kinetic energy do we have right at the beginning of the problem? 0, because we're not moving. And how much kinetic energy do we have right at the end? 0 because we're not moving again. That's right. The block turns around, which means that it's changing its sign of its velocity from positive to negative. Its velocity must be 0, right? So it stops at the end. Okay? Therefore, we have taken care of all of the energy. We have accounted for all of the energy at these 2 points, and now the difference in that energy must be the work done by the non-conservative force. This is a note to me from him?
No, this is a note from Mrs. Humphrey to him, and he said to ask you.
Ah. So, I thought it was canceled, but if we can, then we'd like to.
Okay,
How's that?
very indirect.
Wait, I'll write it down.
Okay, thank you.
Yep. So here is our basic energy accounting. We're looking at the difference in energy between our initial and final states, and that's 1/2 kd squared. That's initial. So 1/2 k1d squared, kd1 squared, minus 1/2 kd squared. And of course, in the problem, we have k, we have d1, we have d. I'm just putting it in symbols here so we don't get lost in the numbers. And that equals the work done by the non-conservative force of friction. That's it. So how do I represent my non-conservative force of friction? Well, for that, I need a... Exactly. And my free body diagram shows mg pulling down, and it shows normal force pushing up, and it shows a frictional force operating in the opposite of the object's motion. And it's also going to show a spring force. But that spring force is not going to dork with our calculations at all. And now I need an equation. Joseph, remind me, how do I compute frictional force?
Frictional force is mu times the normal.
Exactly so. And in this particular situation, what is my normal force equal to? Yep.
Oh, what is that?
It's a killer stink bug.
Oh. That was a bee. Scared me.
And so now it's a simple matter of saying, how much work is done by my non-conservative force? So we need to figure force, distance, and cosine of angle between. We've got force, it's mu mg. It's mu mg. How about the distance?
The spring starts at -5 and goes out to 2.
Yeah. The spring starts here, it goes out to here. Under which part of this path is friction operating?
As soon as it's let go.
All of it, as soon as it's let go. And therefore, the total distance that it travels is d1 plus d2, or d plus d1, yeah. And now finally, the cosine of the angle between. My frictional force, according to the free body diagram, is pointing which way? Left. And which way am I traveling? The right. So what's my cosine of the angle between? -1. That's it. And now I'm ready to solve for, what was I solving for? Mu. Right. I'm ready to solve for mu. I'll divide both sides by -1. And when I divide both sides by -1, that makes this term positive and this term negative. Everybody see what I did there? And I divide both sides by mg. And I divide both sides by d plus d1. And there's my expression for mu. Now, if you actually work this problem, you'd have numbers for all these, right? But I'm just doing this, and the reason I do it like this, and we do this a lot more in AP Physics, is that it actually makes our answers clearer. Because I can look and I can see, hey, look at that. That is the difference in energy between the two states. And that difference in energy is clearly equal to the work done which means that mu has to equal the difference in energy divided by force times distance, or gravity times distance. See what I'm saying? So this is actually a fairly clear answer here. Good. We've got time for one more question if anybody has one. Is this helping you? Good. Question, comment?
Thank you. Thank you. Why do you think it's so fun?
Power, yeah, see, power is one of those sections where we kind of wave at it and we skip by it. I will come back to it when we do.
Teachers, pardon the interruption for another announcement. Robotics with Miss Jong are canceled today. Robotics with Mr. Faisal / Mr. Frankfurt are still on for today. Kids orchestra practice
Yes.
also canceled.
See you later.